So, chapter 2. We're moving on. So chapter 2 is about op-amps. And you should have already used op-amps. You should have already done some things with them. But I'm assuming you haven't really, and you need to work through it, although I'm going to work through some of the stuff pretty quick. Among electronics, they're a remarkably simple, straightforward, easy to use component. They're incredibly versatile. You can do all kinds of things. If you are trying to do something in electronics, the first answer that I would encourage you to always try to answer any question with is, can I do this with an op-amp, right? That's going to be the easiest way to possibly do something. So someone was asking me if they could, they needed a power amplifier. And after you've been through electronics too, it's fairly easy to design a power amplifier with transistors. It's pretty straightforward, and that's a perfectly reasonable way to do it. But my first answer to their question was, well, can you use a power op-amp? And there's such a thing. There's power op-amps that have got arrangements for heat sinks to be attached to them. And they're so simple to use that you'll get wonderful results. And you don't have to mess with a whole bunch of complications with a transistor amplifier. A transistor amplifier may be more efficient or more powerful or more compact or particularly it may be more powerful. But op-amps are so easy to use that if you can use it, that's what you should use. I had a senior project group once completely fail because, well, they did. They had a circuit that was working, and then when they tried to build it on their PCB, it wouldn't work any longer. And the reason it wouldn't work any longer was because they had some extra capacitance and inductance and things that they had to drive, and the chip that they were using wasn't powerful enough to drive that. And unfortunately, they had soldered their stuff in, and they couldn't very easily unsolder it and take it back out to the breadboard stage where it worked, so they didn't really have anything to show. And of course, it happened in the final few days. And when I looked at their problem, it was like, no, you should have seen this problem at the breadboard stage, and all you needed was a buffer. And they couldn't, well, they had a problem because one of the chips they were using was no longer available, so they had one, and they couldn't get a hold of it anymore. But all they needed was a buffer. It was really easy. Any old op-amp would have done just fine for them, and they just needed to build a op-amp buffer, which I'll show you about today or next week. Most of electronics will be looking at the internals of things, about transistor level things, but in this case we're looking at more of a system level applications of op-amps and what you can do with them. Particularly if you're doing the lab with the analog devices ALM 2000 or the digital analog discovery, you don't have a way to measure current. Now, I encourage you to buy a standalone DMM, but and that'll give you some current capability, but it actually won't give you good enough current measurements for some of the things that we need to do anyway. But you have in your kit what's called an instrumentation amplifier, and it is able to give you really, really wonderful measurements of small voltages so that you can measure small currents and small voltages with your USB kit. And that's a fantastic advantage. It's a really simple device. We'll go through exactly how an instrumentation amplifier works, and in the lab you'll start using them. And you will probably use the instrumentation amplifier constantly after you get going with it. So, what is an op-amp? Ideally, a op-amp is a device with two inputs. The book is always drawing it one way, and I always want to draw it the other way, and you see them both ways. I'm just wondering if it's worth my pain to try and write it the way they're writing it. So I guess I'll try. An ideal op amp might look something like that. Where we have two inputs. One we call the inverting input, that's the one with the minus sign, and one we call the non-inverting input, and we'll call these nodes 1, 2, and 3, but often I'm also going to call this V minus and V plus, just because that's a little more easy to understand. And there's an output, V out, or sometimes we'll just call it V naught. That, in its simplest way, this is an op amp, and this output voltage is referenced to ground. So really, we'd measure it down here. Oops. With a ground. And so really, you could consider that we have two input nodes and two output nodes, but one is ground. And we could ground either one of these nodes, and then we'd have one each. So this is the inverting, and this is the non-inverting. And it drives me nuts to say there's an inverting and a non-inverting. I don't know why they do it that way, but the inverting input is very important, so I don't know. At any rate, in the lab, it's very important to realize that there's actually a plus VCC, sometimes it's a plus VDD, and there's a minus VEE, sometimes it's minus VSS, or something else. Those are the power supplies that you have to attach to your op amp. Sometimes there's some other pins too. Sometimes there's a ground, and sometimes there's some pins for adjust the performance of the op amp. We usually ignore those in this class. But if you don't connect and turn on the power supply, your op amp may have some weird kind of characteristic, but it won't be working correctly. Once you turn these on, it will work nicely. And the same exact thing goes if you are simulating it with SPICE. So if you're using LT SPICE or something like that, you have to attach power supplies, and you have to give them a voltage, and you have to turn them on in your simulation, or it just won't work right. Well, if there's a model for precisely the op amp you're using, then you'd be well advised to use that. But if you're trying to do a simulation with an ideal op amp, then the universal op amp might be just fine. But if there's a model for a device that you need, you'll always be better off to use that model.
Okay, thank you.
So we're going to always work with an ideal op amp. Where we have just those pins, 1 and 2 and 3, or V minus and V plus, or the inverting and the non-inverting. And we'll just leave off that power supply. It's assumed that you realize it's there, right? And so don't be confused when you are trying to build a circuit that might have a drawing that looks like this and might not include these things. Don't be confused about that. So what does an op amp do? It amplifies the difference between the non-inverting node and the inverting node. So it's like it's adding them. So V out is equal to V2 minus V1 times a gain. And we could have a gain factor in here of A. It amplifies the difference between those two pins, and it amplifies it by some linear value, A, which should be a fixed number. For the ideal op amp, A is infinite, right? It's huge. Now, in real op amps, the ones that you buy, like the 741, or the ones in your kit, like the OP27 or 37 and stuff, The gain isn't infinite, but it's really, really high. It may be a gain of like 200,000, 100,000, 200,000, really, really big numbers like that. So, and as we go through a little bit more, you realize, oh, okay, the gain on those 25-cent op amps you can buy actually is a lot like infinite. It's really, really huge. And that's critical to making circuits that work right. So really, this circuit really, if I ignore VCC and VEE, all these nodes here are really referenced to ground. And if I really draw it out a little more carefully, then I would have something like this. That's pin 1, that's pin 2, and 3. I never am able to draw a very nice triangular op amp. And as much as I try over and over, it never comes out right. I'm always thinking there's some magic on how I can do this. Oh, now I made a lousy amplifier. It's a little bit better. And it's important to notice that well, what we have inside there is A times V2 minus V1. That's what the this voltage source, this ideal voltage source in there is multiplying A times the difference between V2 and V1, and that's actually what's appearing on the output. So there's no output resistance on that amplifier in there. So an ideal op amp draws no current from its terminals. There's no current going into either terminal. That's really, really useful. And that means Rin is infinite for both of these. For the inverting and the non-inverting pin, the input resistance is infinite, and the output resistance is a short. So it's an ideal voltage amplifier, amplifying the difference between the two pins. Now real ones do really well. They're not quite as good as this, but they do really well. The old ones, like the 741, are made out of BJTs, and their input resistance isn't quite zero, but their ability to output current is quite good, up to a certain point. But their input, they do require some current to come in. Newer MOS ones, and you have some MOS op amps in your kit, have essentially infinite input resistance. All right, there's virtually no current that goes into an MOS at low frequencies, and so they have essentially infinite input resistance. They have zero output resistance up to some output current level, or very close to that, and they have very, very high gain, which is close to infinity, but not infinity, of course. Well, how can we say close to infinity? It's huge. It seems like infinity to us. Real ones often limit output current is maybe 40 milliamps, 30, 40 milliamps, something like that. Although you can get power ones that can output more than that. But often it's like a perfect short on the output resistance until you get to 40 milliamps and it's done. It won't give you any more than that. Which means that sometimes you are actually able to drive an LED directly without burning it up, but don't say I said that when your LED burns up. Now, if ideally, if V2 equals V1, then V2 minus V1 equals 0. So then V out, which is V2 minus V1 times A equals 0. That's the ideal situation. How would that happen? Well, if you shorted together the two terminals and connected them together, then you would have an output of 0. They would have the same voltage on them, and that would be 0. You could connect both of the terminals to a different voltage, to 1 volt or 2 volt or 3 volts. And if you can connect both terminals to 3 volts and there was no other variation, then the output would be 0 because they both had the same voltage. And this property, we call that common mode rejection. And we can define a common mode gain. What did I say? 1 and 2. You can define a common mode gain zero. We could say that we're entirely rejecting the common mode, the common signal. Whether it was 0 volts, it's common to both of these. If we connected both these to 5 volts, the output should be 0 because we have 5 volts here and 5 volts here. 5 minus 5 is 0, and we would have an output of 0. That would be the ideal situation. Shouldn't use that large eraser. It might actually be, the common mode gain might be something more like minus 80 dB or more, which would mean that the output common voltage would be 0 times 0.0001 times VIN, right? It would be 1,000th or 10,000th or 100,000th of the common mode input voltage, but it might still exist there. If it was 1,000th, we had 5 volts on the input, then we would have 1/1000th or 5 millivolts on the output. And actually, that seems like a big number. It is, and so we actually want common mode gain that's 80 dB, 90 dB, numbers like that. So this ideal op amp here is a differential input. We could say these are differential inputs because we're amplifying the difference between these inputs, and a single-ended output because we only have one wire coming on the output. We're referencing it to ground, of course, but it's a single-ended output. In a system, so this is a differential in, single-ended out. Used in systems, it's often fully differential. Which means that we have two outputs and two inputs. So that the output is, or the input is a differential voltage, and the output is also a differential voltage, and it's just amplified. Often this is what's really used in a system, and you've got these in your phone and in your computer and all over the place.
I have a question.
Turn the peanut gallery off. The question is, are we ever going to use a two output one? Not in this class, not in the labs. I don't think your lab kits have any. When I say in system, so usually that's an integrated circuit level kind of thing. What's designed inside an integrated circuit is often fully differential the whole way. Sometimes there'll be differential as in chips, differential level, but that's not near as common. But when you're actually designing the things inside of a chip, which is where almost all the op amps are in the world, those are often fully differential the whole way. For the most part, it's just a sort of added complication, so it's not that big of a deal. Why would you want to use differential in and differential out? If that is the question, why would you want to use differential in and differential out? There's a number of advantages of being differential input, for instance, and a big one is that you reject common mode things. And one common mode thing that often exists is noise. So if you have 60 hertz noise, it often affects both wires on these two inputs exactly the same way. So it's common, and you subtract out that noise. There's lots and lots of clock feed through and all kinds of other things. If these inputs are physically close, often they have exactly the same noise. And when you subtract them, that noise goes away. But as soon as you make it single-ended, you now run the risk of bringing that noise back in. So if you keep both the inputs and the outputs single-ended, then you reject that noise and you just keep rejecting it on through the system. And you might have many stages. You might have several op-amp stages and various other things. And so it's often more useful to keep it fully differential both directions. And principally, that's for common mode rejection and for getting rid of noise. But there's some other reasons too, I think. So what is A? This gain here, A, what is that? Well, gain is always, why would you want to amplify the difference between two signals? So think about what a voltage is. What is a voltage? If I draw a battery here and say this is 1.5 volts, that battery, if I asked you what's the voltage on this battery, you'd say it's 1.5 volts. But what you're really saying is it's the difference between this terminal and this terminal. And often what we do is ground one side and assume that one side is at 0 volts. That's often what we do. But in fact, a voltage is an energy, and energy, just like voltage, means nothing without a reference. You have to have a reference. So we often use earth and assume we're using earth and ground as the reference. Well, we could put one or both of these terminals at ground, and in fact, if we did that, if we grounded one of these terminals right here, can't get that pointer to always show up. If we grounded that terminal, then we'd have a single-ended output, which is exactly equivalent to what we have here when we ground that. So often the reference we often use is ground, but it doesn't have to be. And inside signals, or inside wires and signals, often the reference is not ground. Often we are looking at the signals compared to each other. So one example that you might be familiar with is LAN cables, Ethernet cables. So those are all sort of a plus and a minus. They're all exactly this configuration where we, where we have a plus and a minus. And what we actually look at, the LAN signal is actually the difference between those two. And a Ethernet kind of system is fully differential the whole way through. And in fact, twist those wires together, and that helps reject the noise, because if you do the right-hand rule, you've got the magnetic field going one way on the signal going this way, and you got another signal going this way, and those magnetic fields are opposite each other, and you reject a noise between those two. So I hope that's the answer. We're in fact always amplifying the difference. We never have a signal which is just 2 volts or 2 millivolts or 3 millivolts. It's always referenced to something else. And sometimes we want to fix that at ground, sometimes we don't. Sometimes we want to let it float and be all over the place. So in fact, that's what all signals are. They are a difference between two things. So the gain is V out divided by V in, and V in is just V2 minus V1. So we have V out over V2 minus V1, and that's the differential gain.